As the name indicates, arc length refers to the length of part of a curve. We'll get to curvature in another video. In previous work, you would have seen that the length of a curve given by parametric equations x equals f of t and y equals g of t for t going from a to b is L is equal to the integral from a to b of the square root of f prime of t squared plus g prime of t squared dt. And that can also be expressed in Leibniz notation as the integral from a to b of the square root of dx dt squared plus dy dt squared dt. This extends the way you would expect in R3, where in addition to f prime of t squared and g prime of t squared, we have h prime of t squared, or in addition to dx dt squared and dy dt squared, we have dz dt squared. Using vector notation, this is L is equal to the integral from a to b of the magnitude of r prime of t dt, and that expression works whether we're in R2 or R3. Let's see this in action. For the curve r of t equals 2t, t squared, 1/3 t cubed, find the length of the curve for t going from 0 to 1. Well, r prime of t, actually, you know what? You have the formula right in front of you. I'd like you to pause the video and find the arc length for this curve. To get r prime, we differentiate the components of r, and so we get 2t, and t squared. Squaring those and adding them together to get the magnitude of r prime gives us t to the fourth plus 4t squared plus 4, which factors actually into t squared plus 2, the quantity squared. Since it's inside of a square root, of course, the square root and the square cancel out. We get t squared plus 2. I'll note now that t squared plus 2 will never be negative, so we don't need absolute values for having square rooted a square. Putting t squared plus 2 into an integral from 0 to 1 and using the power rule will give us 1/3 t cubed plus 2t evaluated from 0 to 1. And the arithmetic gives us that L is equal to 7/3. Next, we're asked to find the length of a curve of intersection. And it's the curve of intersection of the cylinder 4x squared plus y squared equals 4, and the plane x plus y plus z is equal to 2, accurate to 4 decimal places. In order to use the arc length formula, we will need to parameterize the length of, or parameterize the curve of intersection. I'm going to start with the cylinder equation. For the equation of the cylinder, the trace in the xy plane has the equation x squared plus y squared over 4 is equal to 1. We recognize that as the equation of an ellipse that is vertically oriented, and a is 2 and b is 1. Now, it's not necessary to draw the ellipse. I'm just doing that for a visual aid for you. But when I see x squareds and y squareds in equations, I'm thinking about sines and cosines. And in this case, it'll make sense, I hope, that x is equal to the cosine of t and y is equal to 2 times the sine of t. If we solve the equation of the plane for z and then replace x and y, we'll have z in terms of t as well. So we have z is equal to 2 minus x minus y. And using the substitution here, we have that z is equal to 2 minus the cosine of t, because that's x, minus 2 times the sine of t, because that's y. The three of these together, x in terms of t, y in terms of t, and z in terms of t, will give us our r. And in fact, r of t is equal to the vector cosine of t, 2 times the sine of t, 2 minus the cosine of t minus 2 times the sine of t. That's the curve of intersection between these two surfaces. We need t to go all the way around the edge of the elliptical cylinder. And so t is going to be between 0 and 2 pi. Now we have what we need in order to find the length of this curve. I'd like you to pause the video and get the integral set up and then come back. Our derivative vector function is negative sine of t, 2 cosine of t, sine of t minus 2 cosine of t. Squaring that and then collecting like terms gives us that the magnitude of r prime of t is equal to the square root of 2 sine squared of t plus 8 cosine squared of t minus 4 times the sine of t times the cosine of t. When I put that into the integral, I just used a double angle formula. Instead of writing 4 times the sine of t cosine of t, I have negative 2 times the sine of 2t. Our integral was originally to be evaluated from 0 to 2 pi. And as you can see, the square root of a 2 sine squared of t and an 8 cosine squared of t with a negative 2 sine of 2t is not something we can easily integrate. And I'm pretty sure the author intended that we would use some sort of computer algebra system. Some folks have graphing calculators that will do the work for them. Great. I'm going to show you how to use something called wolframalpha.com. We can type in integrate the square root of 2 times the sine of t squared, 2 times the sine of t with parentheses wrapped around the whole thing squared. And I'm actually typing this out to show you that as we type in the parentheses, really, Wolfram Alpha is helping us out a little bit. So I've typed plus 8 times the cosine of, that open parenthesis is now in pink. And then the argument t I'm putting in parentheses as well. And that green is telling me, hey, these parentheses have now closed. Close the parenthesis for the cosine of t and now square that. And then minus 2 times the sine of 2t. End the parentheses for the square root. And then we can simply type from 0 to 2 and then pi for pi. Hit enter. And what it does here is it gives you the integral. It says, I think you mean from 0 to 2 pi, this square root. And then it gives the answer as well. It somehow disappeared on me there, but the answer here is 13.5191. That's accurate to 4 decimal places, and that's what we're after. So L is approximately 13.5191. Folks, for most of the work we're going to do, I'm going to want you to do the integrals by hand, but this was prohibitively difficult, and so I do want you to be aware that that tool does exist.